This is Hess's Law. A lot of people like Hess's Law. Hess's Law is rather simple. And basically, what Hess's Law states is if a process can be written as the sum of several stepwise processes, the enthalpy change of the total process is equal to the sum of the enthalpy changes for the various steps. Okay, deep breath. What? Okay, what this basically says is if you can do a process or a reaction in a series of steps and you know the energy of each step, if the steps sum to give you the reaction you're looking for, then you can add those values up. So if we look at step 1 and step 2, and we can see that z cancels out, and when z cancels out, we can add them together. You treat the equal sign as if the arrow as if it's an equal sign. Don't write it as an equal sign. So what happens here is, for example, if this first step is 10, and the second step is 5, then the overall step is 15. Now, if this one's not negative 10, this one's 5, then this value is negative 5. So that's basically all you're doing. Note that the species must cancel out in sum. It is just like a math equation. And we're to the ugly A word, algebra. And the math equation is basically how we're treating those. So this is a series of steps in order to do this. And a lot of people really like these because they're kind of fun and simple. So here we go. Calculate the following using the data. Okay, so this is our goal. This is the equation we're aiming for. So you can call this the key to it, it's the goal, it's the end result, whatever. Now, when you do this, again, there are multiple ways to do the math, as long as you obey the rules of mathematics, and it really boils down to writing them down or not writing them down. So, we're going to work the first one, and I'm going to show you both ways, and I'm going to work them in the detailed form. Some of y'all are going to do it the other way, and I'll show you in just a second. So, the way to work this is the easiest thing is left to right. So, we notice that this first step here has the C2H6. But we have it on the reactant side, which is where we need it. So we're going to leave it alone for that. But our goal only has 1. Here we have 2, so we're going to have to divide it by 2. And remember, what you do to the equation, you're going to do to the delta H value. So I'm going to rewrite it. So it's C2H6. I'm going to be lazy, and 7 halves. Oxygen, and I'm not going to write the states in. I really should, but as long as the states don't come in to cancel, I'll be fine. And I am going to check my, okay, I just wrote that one in there. I'm going to check my math here and say, okay, 2, 7 halves, 2, and 3. Okay, so I'm good there. So I would have to divide this value by 2 as well. And so when we divide it by 2, we're going to get a negative 1559.7. Again, this is still kilojoules, so negative 15,597. All right, so we go to the second step. Well, in the second equation, we need this species, but we need it in the products. So we're going to have to flip this one, and it's one step, so that's all we have to do. And I'm going to go ahead and line up my arrows. And so I'm going to write 2 CO2 plus 2 H2Os yields C2H4 plus 3 O2s. And we didn't do anything in multiplying or dividing, so all we have to do is flip the sign. So again, we're just flipping it, so we would get a positive 1410.9. Okay? So now we're looking at the last step, and the last step contains hydrogen. Well, in our goal equation, we have hydrogen in the product side, so we're going to have to flip this, and we only have 1 hydrogen, so we're going to have to divide this one by 2 as well. So this equation both gets flipped and divided by 2, so again, I'm going to keep my arrows lined up. So I've got H2O now, and I've got H2 plus 1/2 O2. So we're going to flip it, so it's now going to become positive, and we're going to divide it by 2, so it's 285.83. So 285.83. So if we total it, we're going to get 137.03 kilojoules. So this is 137.03 kilojoules. All right, so, oh wait, one question. Is it endothermic or exothermic? It's got a positive, so it's going to be endothermic. So it's an endothermic reaction. Now, this is basically worked two ways. You can work it like I did down below and rewrite everything, and that's how I'm going to set it up. But some people will only do the stuff at the top, and that's fine too. On a written problem like this, you would strictly work it accordingly. On D2L, I might ask it in a multiple choice. I may split it up. I may not. Not sure how. Now, there should be a couple of these in the videos, but I know there are several in the back of the book, and I highly recommend you look at those because they're usually pretty good. These are a little complex, so to come up with the equation stuff is a little bit difficult. So I usually let the book do it. And the trick is keep up with the signs. So a lot of people like these because, yes, it's math, but it's kind of fun math. So we're going to do another one. Calculate the following using the following data. So again, this is where we're aiming for. So our first equation has the carbon plus the O2 gas. Okay, I'm writing states on this one. CO2 gas. All right, it's on the reactant side as 1. So basically, we're not doing anything with it. We're going to multiply it basically by 1 or nothing. Write it as is, whichever one floats your boat. Now, on the second equation, we need the CO2 on the product side. So we're going to have to flip this one. And we've got the CO, and that gives us CO2. And, oh wait, that just gives us CO2. And the oxygen goes in on the product side. All right. Now, wait a second. You know, I didn't cancel this equation. And y'all let me get away with it. Ha ha ha. How can you stop me? Okay, that's 7/2 oxygen. No, actually we have 3 oxygens here, 3 oxygens there. We have 2 CO2s, 2 CO2s. 3/2 is the same as 7/2. So when we're done, we should end up with the correct equation. Sorry, guys. Don't know what I was doing there. I was getting too excited showing you how to do the shortcut. And remember, shortcuts will get you in trouble if you don't understand the long cut. So the net effect is if we could total them to get the equation we're looking for, life is good. So we're going to flip this one so it becomes 283.0. And now I'm going to add it. Wait, CO2, yeah, we're good. So notice the CO2 cancels. Half of oxygen cancels, so I'm left with half of oxygen here. So I end up with carbon plus half of oxygen is equal to CO. Now, notice that when I was working this, I didn't worry about the oxygen. I worried about the carbon species, the ones that are like compounds, because you have oxygen in different forms in both. If you worry about the compound, there I go yawning again. Excuse me. If I worry about the compounds, then the oxygen usually takes care of itself. So in this case, we're going to add these together and we get 110.5 kilojoules. This one is an exothermic reaction because it is negative. All right, let's do another one. We'll try to do this one right. Again, this is the equation we're aiming for. Now, on this one, we happen to have the NO in the third equation. So I'm going to write it first so that it's easier to see. We have ozone plus NO2 plus O2. And we didn't do anything, so we're going to keep the 199. So we just as is. All right. Now, on the next one, we need oxygen single. Well, this equation is the only one that has oxygen single, but it's on the wrong side. It's on the product side, so we're going to have to flip it. And we only need 1, so we're going to flip it and divide by 2. So we'll get oxygen yields half oxygen. So it's, I forgot to divide it by 2. So we get a negative because it was positive. So it's negative 247.5. And again, we could have divided it by 2 and flipped. So it'd be negative 247.5. This one was left alone, so it's 199. So if you look at it, we've gotten rid of our, we've gotten rid of nothing, but we've added in our oxygen. So now we've got ozone that's got to go and oxygen that's got to go. But let's worry about the ozone. So we need ozone to be gone, which means we got to have ozone in the product. If that's the case, we're going to flip it. And we only need 1, so we're going to flip it and divide it by 2. So we're going to get 3 halves oxygen goes to 1 ozone. And so if we flip it and divide it by 2, then we're going to end up with a positive because it was negative 213.5. So if we look at our equations, we have O3 is gone. We have 102 and a half, so that's 1 and a half, which is the same thing as 3 halves. So our O2's cancel, so we're left with NO plus O yields NO2, which means if we do the math, we end up with 233 kilojoules. Again, this is an exothermic reaction. So up here, it would have been 213.5, and we get negative 233. Now, do you have to do both? No. Some people are only going to do the top. Some people are only going to do the bottom. So I'm just showing you that you can look at it either way and be fine in doing these problems. Okay? So that brings us to the next step, which is chemical bonds. So when we talk about chemical bonds, energy is always released or given off during the formation of chemical bonds. Okay? So that means that this step is always exothermic. So think about magnets. If you have a north and a south pole, when you put them close enough, they snap together. So it doesn't take any energy for you to snap them together. But on the other hand, energy is always required or needed during the breaking of chemical bonds, which this makes sense. You have two magnets together, you have to pull really hard to separate them. So this is an endothermic process. So now the trick is wait, that would mean that reactions are always exothermic. No. Some of them are endothermic. The bond formation may always be exothermic and the bond breakage may always be endothermic. But it's kind of a function of how much energy you put in versus how much you got back. So basically what it boils down to is the change in enthalpy of the reaction standard. It's going to be the products minus reactants. Remember, that's always final minus initial. Well, in a chemical reaction, initial or reactants, products are final. So that's what we're looking at. So when we look at the values, etc., what it boils down to is if delta H is negative, more energy is given off by the bonds forming in the products than needed to break the bonds. So delta H of the products is higher energy than delta H of the reactants. So in this case, this would be an exothermic reaction overall. On the other hand, delta H will be positive when more energy is needed for bond breaking in the reactants than given off or released in the forming of the products. So in this case, your delta H of products is less than that. So this would be an endothermic reaction. So if more energy is required to break the bonds than you get out from forming the bonds, then it's endothermic. If you release a lot more energy than you needed, then it's exothermic. Okay, so that brings us to enthalpy of formation. That's the energy of reaction in which one mole of pure substance is formed from the free elements in the most stable form under standard conditions. Now, this is delta H, standard of formation. That's what the F is formation. And you can find these in the appendix. You'll have some of these in mastering, and they will have a table for you to use. Okay, so let's real quick talk about standard state enthalpies of formation. You have to worry about the amounts of reactants or gases, temperature conditions, and the physical states. Because the formation of elementals like O2 gas would be 0. However, if you have O2 liquid, which yes you can, then that's not going to be 0 because that's not the standard state. Now, this is the thermodynamic standard state. Remember, STP for gases was 1 atmosphere of pressure and 0 degrees C. In thermodynamics, it's still 1 atmosphere, basically. It's 1 bar, technically, in both. But it's now 25 degrees C. Why? This is room temperature. For gases, it's 0 degrees C. But for for enthalpy, you're doing room temperature, and it's designated by the little degree symbol. So, how would you use it? If you're given a reaction, for example, given here, then what you would do is remember these are the products. These are going to come first. These are the reactants. These come second, because it's always products minus reactants. And so you have 3 of the C's, 4 of the D's, 1 of the A's, and 2 of the B's. So you have to take into account the coefficients. Now the other trick is that this is math. Be careful, because if you end up, for example, with a negative value here, a negative value in between, and a negative value here, if you have a negative on a negative, remember that becomes a positive. So if you actually do the math here, you get 141 kilojoules per mole, and it's positive because you have a negative on a negative. Okay? So this is actually really simple. If you use Appendix 3, we're going to solve this using this equation here. And so the solution comes out looking like this. Is products minus reactants. So we would look up the the products. And again, you can label them at the top and then use them, or just put them in. It doesn't matter. Just make sure your products are grouped together and your reactants are grouped together, and your products come first. So these happen to all have a coefficient of 1, so we don't have to do anything with that. So as we do the math, we end up with a negative on a negative. So we end up with an endothermic reaction when we're done. And it's relatively simple to do. It's just a matter of looking at the values. Now, here's another example. You could look this one up in the Appendix B for the values. However, I'll be honest, I've kind of put too much material on this exam, so I've got to dump something. We'll see this again later, A and B. I've done a number of these in mastering, so you've actually already done that. So if it shows up on the exam, it will be something really, really simple, like, I don't know. But it'll be really, really simple. Odds are, if I'm going to dump something, I'm going to dump that problem. Okay, now, scientific and political challenges of biofuels. This is actually interesting to read from a scientific viewpoint, because what they're talking about is when you're making biofuels, and biofuels are things like ethanol, You can make ethanol from sugar cane. You can make ethanol from corn. Primarily, it's made from corn in the Midwest because we have a lot of it. The problem with it is that because the corn that would normally go to feed people starving in other countries is now going to ethanol, it's not going out. So the question is it better to make the biofuel or is it better to feed people? And there's huge debate about this, and you can take either side you want. The bottom line is you just need to understand what the ramifications are. Now they're working with sugar cane here, and actually, this is kind of funny. We live in the South. Kudzu roots have a lot of sugar in them, and they make fabulous ethanol. The problem is you really can't get to the roots because they tend to be 6 feet deep, and so you need a big kudzu patch, which that's easy to find, but then you have to excavate the roots out and everything else. So again, with anything else, there are side effects, positive and negative. So read through food and fuels, and again, it probably will not appear on the test. However, you are citizens of the United States, and we interact with people all over the planet. So therefore, you might want to look at this section so that you understand both sides of the argument, or at least understand the terminology. All right, now we're at the end of this chapter, so we're done with chapter 6. Chapter 7 and 8 will probably go up tomorrow. Some of them may go up today. As I said, there's a lot on this chapter. The beauty of that is that things will be spread out. The ugliness is there's a lot of stuff on this chapter. However, the next 2 chapters have basically one math problem in it, and the rest is non-math. And so people who don't like the math are excited because there's a lot in these 2 chapters so far. Okay, not the gas laws. But in thermo, there's some definitional stuff. So those of you who are not math crazy nerds, like some of us, are usually happy with these sections. So we'll continue on in the next chapter in the next lecture.